Let us do a quick recall of what we understood in the previous videos. We are trying to prove the division algorithm. It says let a and b be integers with b is greater than 0. We know this. A division by 0 is not defined. Then there exists unique integers q quotient and r remainder with the property that a is equal to b into q plus r, where 0 is lesser than equal to r is lesser than b. We know R is less than B. If we plot the divisor on a number line, then we can find out that remainder it is less than the divisor. Um, Although we have an alternative proof for R is lesser than B, this you can check in the preceding video. Now I will read it out, and if let's say you still have a difficulty of getting a hang of the proof, then my advice is that you try you try going through the earlier video at least two times. Then it will be amply clear. Conceptually, it will be clear what is written here. Now let me simply read it out. Proof. We begin with the existence portion of the theorem. Consider the set S is equal to A minus B into K, where K is an integer and A minus B into K is greater than equal to 0. If 0 belongs to S, then B divides A, and we may obtain the desired result with Q is equal to A by B and R is equal to 0. Now assume 0 does not belong to S. Since S is non-empty, if A is greater than 0, A minus B into 0 belongs to S. Why we took K is equal to 0? Because the net result has to be greater than 0. Now, if a is lesser than 0, a minus b into brackets 2a is equal to a into brackets 1 minus 2b belongs to S. Why we took the value of k equal to 2a? This is because the net result it has to be greater than 0. We know that set S it has non-negative integers. A is not equal to 0 since 0 does not belong to S. And um, yes, this is how we proceeded with the proof. We may apply the well ordering principle to conclude that S is the smallest member, say R is equal to A minus B into Q. Why we say this? Because S is non-empty, so that is why S has the smallest member. Say R is equal to A minus B into Q, according to the well ordering principle. Then A is equal to B into Q plus R, and R is greater than equal to 0. So all that remains to be proved is that R is less than B. We also saw the proof of how we derived R is lesser than B. You can check the previous video. It has a thorough proof. Now let's quickly finish what remains. To establish the uniqueness of Q and R, let us suppose that there are integers Q, Q, one more Q, R, and one more R, such that. Let me go to a different slide. It will have a better visual representation. We still have to prove that Q and R are uniquely determined. To do this, we suppose that A is equal to B into Q1 plus R1, and 0 is lesser than equal to R1 is lesser than B, and A is equal to B into Q2 plus R2, and 0 is lesser than equal to R2 is lesser than B. For integers q1, q2, r1, r2, we must show that r1 is equal to r2 and q1 is equal to q2. If r1 is not equal to r2, without loss of generality, we can assume that r2 is greater than r1. Subtracting these two equations, we obtain 0 is equal to a minus a. We are subtracting, so a minus a is equal to 0 is equal to, we also subtract the right hand side. We know this. This is simple maths. So I'm assuming that you stay with me on this. BQ1 plus R1 minus BQ2 plus R2 is equal to B brackets Q1 minus Q2 plus brackets R1 minus R2. This implies that R2 minus R1 is equal to B brackets Q1 minus Q2. What we did in this expression, we brought this R2 minus R1 to the left hand side is equal to B into brackets Q1 minus Q2. This implies that B is a divisor of R2 minus R1 by theorem 10. So let us quickly go through this. It's loading. 10, it says if d and n are positive and d is a divisor of n, then d is lesser than equal to n, comparison property. This is easy to understand. This implies that b is lesser than equal to r2 minus r1, but since 0 is lesser than equal to r1, and we did assume that R2 is greater than R1. So R1 is lesser than R2 is lesser than B because B is the divisor. Let me read it again. But since 0 is lesser than equal to R1 is lesser than R2 is lesser than B, the divisor, we have R2 minus R1 is lesser than B. How did we derive this expression? Uh, we know this that R2 is less than the divisor B. And if I subtract R1, it will still be lesser than the divisor B. This contradicts the earlier result we had obtained here. B is lesser than equal to R2 minus R1. So we must conclude that R2 is equal to R1. Now from 1.5.2 here, we have 0 is equal to B into brackets Q1 minus Q2. Why? Because now we have concluded that R1 is equal to R2. So if these two values are equal, then R2 minus R1, it has to be 0, is equal to B into brackets Q1 minus Q2. Since B is greater than 0, this tells us that Q1 minus Q2 is equal to 0. That is, Q1 is equal to Q2. We have 0 is equal to B into brackets Q1 minus Q2. Since B is greater than 0, we know this. This tells us that Q1 minus Q2 is equal to 0 because we have two multiples B and another is Q1 minus Q2. B is not 0. So the other one, it has to be 0. Q1 minus Q2 is equal to 0. That is, Q1 is equal to Q2. This completes the proof of the uniqueness of R and Q in 1.5.1. Here we started. So it proves the uniqueness of remainder R and quotient Q.